Hello everybody and welcome back to the 2003 Euclid. It's Root Beer here. We're looking at question number 9. Cyclic quadrilateral ABCD has AB is equal to AD is equal to 1. CD is equal to, that's weird, cosine of the angle of ABC. I'm sure that'll play somewhere in there. I just don't usually see angles equal to cosines, but whatever. And the cosine of angle BAD is negative 1/3, so that's going to have to be an obtuse looking angle because it's a negative cosine. Prove that BC is a diameter of the circumscribed circle. So it is a cyclic quadrilateral, so being cyclic, the first thing we should probably do with it is draw a circle around it. How do I want to lay this thing out? So let's go over and draw ourselves a picture. So we want BC to be the diameter. So let's draw ourselves a diameter, and actually, let's draw ourselves a circle, a decent-looking circle first. That's awful. That's a little better. Let's try one more time. I'm always wide on that one side. Okay, so we got our diameter. This is the picture I'm sticking with because it's the least bad one I've done so far. So BC, what else? We've got A, B, C, and D. We have to place A and D as well. BAD is going to have to be a obtuse angle. So I guess the B, A, and D are probably going to be pretty close to each other on the circle. AB is equal to AD, so A has got to be between B and D. So if I were to place, I don't know, B or D up here, A would have to be in between here. That creates a nice obtuse angle. And those two must be the same, and we just connect C up with D. Okay. So things to note, these are side lengths of 1. I want BC to be a diameter. It looks diameter-ish, but can we prove that? We were also told CD is the cosine of ABC. So maybe it's a good idea to draw that line right there. So this is going to be cosine of ABC. I still think that's really weird. Okay. And the other piece of information, which we can't really label on this graph, is that BAD, it was bad, right? BAD has a cosine of negative 1/3. So I guess we can add in, with dashed lines, this triangle right here. So triangle BAD. Now I'm given two cosines, and cosines to me suggest trigonometry. And specifically in terms of trigonometry and figuring out relationships, I tend to think either we're going to have a right angle triangle somewhere so that we can use SOHCAHTOA. And so somewhere in there, one of these two cosines will come up. Or the cosine law. That's the other way that I think cosines might pop in here. Okay, so to show BC is a diameter, and I think we actually mentioned this in problem 8a, it would suffice to show that we've got BC is subtended by a right angle. And we've got a couple candidates. In fact, they will both have to be right angles if BC is a diameter. But we would like to maybe show that maybe BDC is a right angle, or maybe we can show that BAC is a right angle. Maybe one of those two can be shown. Okay? And then that would show that BC is a diameter. I suppose the most immediate thing would be we can work out what BD is. Using the cosine law, I don't see where this is going to help us, but using the cosine law, BD squared is AB squared plus AD squared minus 2AB AD cosine of angle BAD. And we know all three of these things. This is 1 squared plus 1 squared minus 2 times 1 times 1 times negative 1/3. And so that's 2 minus 2 times negative 1/3. So that's 2 plus 2/3. And that is 8/3. Okay. So now we know what BD is. Congratulations. Let's label that. But I don't see where that's going to help us. It's a nice exact number, sure. Well, we've got cosine of angle ABC. Should we use another cosine law somewhere in here? We'll draw this triangle. Oops, wrong color. I was using the yellow. So we have that one in there. I suppose we could work out AC in some fashion, but we'd have to know what BC is. And I don't know as the length BC is going to be useful to us. Okay. Right now, we don't have any clue about what length AC should be. It's got to be related in some way to DC, because we could use the cosine law and just give BC a name like D for diameter or something like that. So I don't think we want to focus on triangle ABC. I think we'll probably have to use both triangles at some point. But right now, I'm more interested maybe in BDC. I think it's closer to showing that it's a right angle. Because we got one of the lengths. We have cos ABC, so we have some information about DC. And I think we're going to have to label BC in some fashion. And then show that BC squared is BD squared plus DC squared. And then that would show, by Pythagoras, that we've got a right angle. Okay. We're not given any other information, are we? Cyclic quadrilateral, that's fine. The only other thing I could think of is if it's a cyclic quadrilateral, we can figure out its area by a modification of Heron's formula, but that's not really going to help us, I don't think. Because we don't want to add in any area. That's the only other thing I can think that might have any relevance here, but I'm pretty sure it doesn't. Oh, I think there's another piece of information we might need. What? I just can't draw circles today. What is this? I should keep a coffee mug with me so I can always just put it on the tablet and draw. But I believe if we have, that also doesn't work. If we've got a cyclic quadrilateral, as I recall, opposite angles have to add up to 180 degrees. So that might be useful as well in some fashion. Oh, okay. Yeah. So opposite angles have to add up to 180 degrees. So since A, B, C, D is cyclic, then angle BAD plus angle DCB must be 180 degrees. Okay, so we've got that. But we know the cosine of BAD. So negative 1/3 is equal to the cosine of BAD. And that, of course, is the cosine of 180 degrees minus DCB. And there's an identity in here somewhere. I think that means that that's negative cosine of DCB. So that means cosine of angle DCB is 1/3. Hooray! Well, I've got this angle here. This should be a right angle. I haven't proven that yet, but it should be a right angle. And this gives us another relationship between DC and BC, because we can use the cosine law with the 1/3 and the 8/3 to get a relationship between those two. If this were the case, if we will show that this is a right angle, because that's what we need to. But if we jump ahead and if we knew this was a right angle and we called this side, I don't know, x, then this would have to be 3x. And we could actually solve for x because we know that we got an 8/3 here. But that's if we knew we had a right angle. So what else can we do here? I feel like we're one piece of information away. I think we need one more relationship or something. I'm going to call DC. I'm going to have to go over to the next page, so I'm going to redraw my picture again. But I'm going to call DC, what did I just call it? X, I guess. So we have a slightly bigger picture. What was it? A was up like that. D must be up like that. We had that. We know that this is length 8/3. We worked that out. These are both length 1. And I'm going to let x be cosine of ABC. So let this unknown side length be this. If I could show that BC is 3x, I think we're done. So the question is, how would I go about doing that? Because that just used the angle there. We have this 8/3 here. I don't know if that's going to help in some way. But one thing we haven't used is triangle ABC. Oh, because if I know this cosine, then I know this is going to have negative x as its cosine. So since ABC plus angle ADC equals 180, we also know that the cosine of ADC is negative of the cosine of ABC, which is negative x. Okay. So now I've got two ways to calculate AC. Actually, I don't even need to calculate I can calculate AC one way and get it in terms of x. I got a 1, and then I could probably then calculate BC using the cosine law again. Okay, so I think we got it. So AC is AD squared plus DC squared, that's 1 and x, minus 2AD DC times the cosine of ADC. So that's 1 squared plus x squared minus 2x times negative x. So that's 1 plus, the negatives will cancel out, we'll get 3x squared. So that's what AC squared is. And AC would therefore be the square root. But as I'm about to do the cosine law again, I'm just going to leave it like this. And AC squared is also AB squared plus BC squared minus 2AB BC times cos angle ABC. I can't really solve for BC from this exactly, can I? I'll get some equation involving x. So 1 plus 3x squared is equal to 1 squared plus x squared. BC isn't x squared. Doy. I'm going to let y be equal to BC. Anyway, I can just plug that in here. Y squared minus 2y times x. Okay. So we've got that. We have a relationship between x and y. It would be great if I could just... y should be 3x. It should be, I think. Does 3x work in this equation? Because if y is 3x, then I immediately know that we got a right angle at D. So 1 plus 3x squared is 1 plus, I did 3x squared there, and then I went minus 2 3xx. I'd get 1 plus 3x squared is equal to 1 plus 9x squared minus 6x squared, and that would do it. That would solve it. So we're on the right track. We've got the right setup. Now let's just show y has got to be, there's only one value y can be. So we got that, and we know this. Great. The two ones will cancel out. So y squared minus 2xy minus 3x squared has got to equal 0. I'm going to add an x squared, and then I've got to subtract another x squared off of this. Great. Now this is y minus x squared. Minus 4x squared is equal to 0. So y minus x squared is equal to 4x squared. Square root both sides. X minus 4x has got to be plus or minus 2x. Because when we square root, we could have a plus or a minus, and those are both fine. So either y minus x is negative 2x, And that would mean that y is negative x. And that's not possible, as y and x are lengths. Okay, one of them would have to be negative, and that's not possible because we got two lengths represented by these values. Or, now this is the one that has to be true, it's 2x, and that would be y is equal to 3x. Okay, great. So now we know BC is 3x. So let's redraw our picture one more time, and I think we can finally conclude, thanks to that one cosine being 1/3. X over here, 1, 1. Maybe I didn't even need the 8/3. 3x. And I know this has cosine equal to 1/3. And we got A, D, C, B. Okay. I should be able to work from here that I get a D here. So extend DC. And let J be the point on DC so that BJ is perpendicular to DC. So that'll be some point. I don't exactly know where. It might be over here, but it's some point. Okay. That's J. Then since cosine of angle BCD is 1/3, and BC is equal to 3x, we use SOHCAHTOA to conclude that CJ must be equal to x, but DC is equal to x. So D and J must coincide. Therefore, BCD has a right angle at D. And therefore, since this is on the circle, BC is a diameter. And that does it. Okay, so it took us a while, and I never really used that 8/3. That's okay. It was a bit of a red herring. If I had the time, I'd probably go back and clean it up, or at least erase it a little bit, because it didn't really help me at all. And no sense including parts of your proof that you don't use. It just clutters everything up. But if I just ran out of time, I probably wouldn't have time to erase it, and it's okay. I just rambled, and that led to a dead end, but I did get the solution. Okay? And typically, in my experience, we've never taken off marks for extraneous information unless it like really clutters up the page and makes it impossible to read. And I only had one calculation that gave me 8/3, and it really didn't get in the way. Okay? And just double check. Yeah, 9 it didn't have any parts. So we've got 10 left to go, and then this Euclid's all over. Hopefully you've been enjoying it as much as I have, and give 10 a shot before you watch it in the next video. I'll see you guys then.